Lab number 5, presented by Andrea Otero. For experiment number 5, we had to choose our own adventure from the outside world and try to model it by using the fundamental principles and main physical concepts we have been studying throughout the semester. For this lab, I decided to model the motion of a falling slinky, treating the slinky as a point particle system. Using Tracker, I was able to extract the experimental data of the falling slinky, and afterwards I constructed two models in order to model the motion of the slinky. One model only took into account the gravitational force, while the other took into account drag force as well. The model involving drag force was more accurate. I also discussed how the model would have changed if the slinky would have been treated as a multiparticle system instead. Using Tracker, we studied the slinky as a point particle system. In order to do so, we had to track its center of mass as the slinky fell. So I had to count the number of coils, which was 80, and divide it by 2, which is 40, in order to find its center of mass, which was 40 coils downwards in order to be able to track the center of mass as it fell in each time interval. The intervals consisted of 0.033 seconds, and a calibration stick of 1.20 meters was used. This image shows the graph produced by Tracker as the slinky fell. The point showed by the arrow is the point where the slinky fell together as a whole piece, not only the center of mass. The instant is also shown by the image to the left. As we can see, the graph changes a little. In order to construct our models, we used as a fundamental principle Newton's second law, as shown in the slide, in order to be able to predict the future motion of the slinky as it fell. Initial conditions as the mass of the slinky, which was 0.227 kilograms, its initial position, which was 0.008 meters in the x direction, negative 0.0891 in the y direction, and a time interval of 0.033 seconds for a total of 0.53 seconds were defined in the code initially. For the first model, the net force acting on the system was equal to Fg, the weight force. The images show the model running of the predicted motion of the slinky, and a graph representing its motion in the y direction, as it fell. For my second model, I incorporated a drag force to the model as well, meaning that the net force in this case was equal to the weight force plus the drag force. I used the formula of drag force, which is equals to a constant b times the velocity squared. In this case, I had to calculate a b that approximated the best motion of the falling slinky, which in this case was of 1.2. The picture clearly illustrated the model of the falling slinky, and the graph represents its motion in the y direction. Using Google Docs spreadsheet, I was able to construct a graph that compared the experimental motion extracted from Tracker with the two models that were constructed. As seen, the model of the drag force predicted more accurately the motion of the slinky compared to the model that only took into account the gravitational forces. However, there were still some discrepancies between the models as shown. I can therefore conclude that taking into account other forces other than gravity, such as the drag force, constructed a more accurate model, since there is a force on the slinky acting upwards, which prevents the slinky from accelerating so much downwards if gravity were the only force acting on it, as we can see in the graphs. The models I constructed do not represent how the bottom of the slinky remains stationary like in the video, because we treated the whole system and the whole slinky as a point particle system, taking into account the center of mass of the complete slinky. Therefore, we modeled how the center of mass of the slinky moved, which it did since the beginning, which was at the 40th coil, and modeled such movement. However, if we treated our system as a multiparticle system, things would change in the model. We could divide the slinky's mass into 3 parts, assuming there is a center of mass in each of the parts, in order to model how at the beginning only the first section would move, while the other two remain stationary, and then the second one, followed by the third one, would fall, as the force exerted by the hand into the first section propagates downwards, sending the signal to the lower sections, until the 3 sections will move together downwards. Since it takes time for the first section to send the signal to the other two, the bottom part remains stationary meanwhile. Here we can see some pictures of this situation. Thank you for your time.